many of you guys already know like Eric. So, but next talk will be about PyWren, and Eric is a postdoc in Rice Lab, also a very senior member in both M Lab and Rice Lab. So, his research areas is in machine learning, scalable computations, and computational neuroscience, right?
Yeah.
Okay, thank you.
I'm not sure how I feel about being described as a very senior member, but thank you for the lovely introduction. You guys actually the overview was so great that I feel like it may have contained some spoilers, so I'll skip past some of the material here. But right, so I'm a postdoc mostly interested in kind of how scalable compute and machine learning can accelerate science, right? And by science, I mean kind of everything that brings, we used to, I used to say that I'm very into kind of data science for scientific applications, or as we used to just call it, science. The interesting questions that you run into these days in a lot of scientific computing domains look very different from what we've historically seen in a lot of the big data analytics challenges. Because in science, often acquiring the data is very expensive. Often kind of making experiments takes a lot of time or a lot of graduate students. And so if you either have limited money or kind of any compassion, you might want to very efficiently acquire certain types of data, which suggest different types of models and different roles for computation. But PyWren grew out of this. So I'm going to give a bit of a PyWren overview. A lot of you have already seen this. This has kind of been in the press. I'm going to talk about some of the upcoming improvements that we're planning, and then talk about ways that we're trying to go kind of beyond map, right? And kind of hopefully embrace understand what other sorts of novel computing paradigms might work on, or novel computing approaches might work on these kind of serverless architectures, right? Now, the goal of PyWren was very much to kind of build a cloud button, right? Thank you, Shutterstock, for already having this photo available for $10. But the goal is for people who are neuroscientists or are doing microscopy or doing geophysics or astronomers or people doing finance applications or even developmental economists, these are people who maybe can't necessarily easily jump on kind of the Scala bandwagon. Maybe these are groups that in many ways have large amounts of computing tasks that have been kind of left behind from this kind of distributed computing revolution. And this is part of why we built PyWren. So PyWren kind of has two components, right? There's the research components, and then there's the tool component. On the research side, we're very interested in kind of what kind of real-time scalable and elastic execution enables, right? What happens when suddenly you have kind of real-time access to 5,000, 10,000? If you're very nice to Amazon, they'll raise it to 50,000 simultaneous cores, right? And from a tool perspective, kind of how can we bring the benefits of elastic compute to these sorts of underserved audiences, right? In many ways, if you think about the kind of embarrassingly parallel tasks that you have sitting around in your workflow every day, a lot of them it's just not worthwhile to kind of overcome the activation energy to use something distributed. And we were trying to fix that. Now, this is the easy EC2 comparison page, right? That lets you figure out what type of EC2 instance you want. And the argument's always been for a lot of users, this is just too overwhelming. Kind of getting on board with these sorts of systems is too damn hard, right? And you have to immediately, if you want to start using this cloud infrastructure stuff, make decisions like what instance type, how many do you want to spin up, how large of a cluster you're going to pre-allocate. It gets worse and worse, and then suddenly you're left with kind of a naked Linux machine, right? Which is not great for, again, a lot of these users that we talked about who are very smart people, but perhaps didn't manage to spend the first 4 years of their lives doing kind of computer science, right? So our goal with PyWren was to build a system that would have very little overhead for kind of getting started, right? So we didn't want to have people pre-allocate clusters, and we also didn't really want them to have to think about how they were going to use this. And in fact, we were just targeting anyone who could use Python, right? We'd like for them to be able to target jobs that kind of run in the minutes to more regime, right? Now, there certainly are distributed computation tasks, and we'll even talk about some of those, where kind of that granularity isn't a good fit. But often, the amount of time that you're going to sit there, if you are doing tasks that are going to cause you to go to the different Chrome tab and start reading Hacker News, this might be a good avenue for something that you could parallelize and distribute, right? We didn't want to run a service, so we wanted to take as much advantage as possible of existing compute infrastructure and kind of newer things that were being offered by the cloud providers. And we really wanted to be from a cloud provider that was going to give us some sort of academic credit, right? This is the way that a lot of us benefit tremendously from Amazon, Microsoft, Azure in actually getting our work done. So we had to work within those frames. So PyWren was, Wren is this tiny bird, right? The goal is to have it kind of be in contrast to a system like Condor, which is this large-scale job scheduling system for traditional HPC. And PyWren's primary interface basically lets you map your function across some data, right? Not terribly complicated, right? So if you have some function, myfuncx, right? You map it, you then call getAllResults, and you get the results. Now that looks very, very simple, and in fact, for a lot of use cases, it is. But what's happening behind the scenes here is that these functions are getting kind of packaged, distributed, sent out to workers on Lambda. And this means that, as the number of workers scales, if you're doing things like matrix multiplication, or if you're doing small kind of matrix multiplication tasks, you can get kind of a lot of aggregate flops from this sort of system, right? And lest you think this isn't very useful, or you're like, well, that's okay, but my use case won't work. That might be true, but we have found a lot of people getting very excited, right? Even to our kind of glorious surprise, Amazon got excited and started talking about PyWren at reInvent. And so the nice thing about PyWren is you can pip install and start playing about it today, and if you have this kind of map level parallelism sitting around in your code, it might be possible to kind of transparently take advantage of it. But where are we going, right? I love this is another stock photography sites are great for presentations of this person looking up to climb into the cloud. Let's talk about some of the upcoming improvements. Now, one of the challenges of using a service like Lambda as the backend for PyWren is that you often have to make a lot of compromises, right? Either in terms of how much compute you have access to, or kind of what kind of functions you can use. And so the improvements we'll be talking about primarily are based around that. And sometimes, Jeff just does these improvements for us, right? So as of 3 days ago, right, AJ, who's the PM for Lambda, said, hey, now you can run functions up to 15 minutes on Lambda, right? Very happy Bezos. And what this means is that before, PyWren was limited to kind of relatively short running jobs, right? And what this meant is, for example, if the task that we were doing needed to consume a certain amount of data from the network, right, that then further limited the amount of compute you can do, and this kind of changes the game, right? And this changes the game in two ways for us. One is that we actually found that a lot of people's intrinsic compute workloads were kind of on the order of 5 to 10 minutes, right? So that tends to be, again, it's kind of the cup of coffee scale that we wanted to enable or parallelize. But two, there's kind of a surprising amount of jitter when you're invoking Lambda functions, right? Not only is there some kind of uncertainty about getting them set up and whatnot, but also you're not necessarily aware of the exact compute hardware that you're running on, which means that maybe it's a slightly faster core, maybe it's a slightly slower core. So what 15 minutes really does is let us very robustly run jobs up to 10 minutes and be very, very guaranteed that they're going to work all the way through. But the other challenge you run into with Lambdas is this notion of a runtime. So part of, scientific computing community goes back and forth a lot. It's kind of this perennial argument where Python's very dynamic, this dynamism is great, it lets you be very expressive, but it also makes it very hard to efficiently compute, right? So for most of the efficient computation you try and do in like the PyData stack, you're calling out to C external C modules, right? Things like NumPy, pandas, et cetera. And that's great, but the code that's running on your laptop, on your Mac laptop, is not the same as the code that's going to then run on some Linux machines, right? They're different operating systems. So kind of transparently moving those over is hard. So we have this notion of a runtime. It's kind of a prepackaged Anaconda environment that we deploy onto inside the Lambda, right? And so at the end of the day, how is PyWren actually doing this? Well, you call map on some function, that data is serialized, it's sent over to S3, we invoke this Lambda, we pull this job from S3, right? So we pull kind of the closure, and then we download this custom runtime that we've built, right? We invoke Python to run the code, meanwhile you're polling back here, this is all fine, but it's this runtime part here then that ends up being an impediment, right? So this is the smallest snake in the world. Very in contrast to the Anaconda that you're downloading from Continuum. But we would like to have kind of all of these scientific Python packages present. And so to kind of cram the full kind of 1.2 gigs down into the limited 512 megabytes that Lambda gives us, we had to go through a bunch of kind of silly steps, right? We're stripping things out, we're deleting things, it's this whole problem. And we barely get under that for just these 4 packages, right? And so the #1 challenge we kept running into with PyWren was we get users filing tickets saying, hey, can you install this module into the default runtime, or you can install that module into the default runtime? Because we have this dream that we'll eventually let users build their own runtimes, but that's still kind of hard. We said, well, The problem is once we start installing all those modules, we blow through this 512 megabyte limit. How might we fix that? And to think about that, let's go on a brief tour. I know this is really what everyone's excited about at 9 a.m. on a Friday, of how dynamic linking works. So if you remember back to your operating systems class, when you're running on a Unix-style machine, you start off and you have an empty process. And the kernel will start, and it will put this thing called the dynamic linker in your process, right? This is the program that actually starts everything up. And one thing the dynamic linker will do is it will find your Python interpreter, right, your copy of Python in user bin, and copy that into your process's memory space, and then start running it, right? And if at some point Python, now these are all very stylized, and there's a lot of simplifications here for kind of pedagogical reasons, but when you call import scikit-learn, right, Python internally calls this function dlopen. So it calls this function inside of your dynamic linker, which goes and finds this shared blob of code, right? This blob of C code, in this case called sklearn.so. There's not actually an sklearn.so. It's a bunch of different files, but whatever. It finds that, and then it copies it back into your process space, and then your Python interpreter hands off control, and you do that to, do k-means or whatever it is you're using scikit-learn for, right? Now, that's great, and it really works, but it requires this scikit-learn SO to already be on your disk. And what happens when you find yourself wanting to, use numba? So you have to have the LLVM shared object. If you want to use pandas, or if you want to use scikit-image, or if you want to use FFT, or you want to use MKL, right? Suddenly you're kind of blowing up in space. And in fact, if you just look at the contents, right, the per file type contents, if you build a runtime with all the packages you can imagine wanting, you got 1.6 gigs of shared objects, right? Of just binary shared objects. Then another 120 megs that are Python binary or Python source files. You've got some binaries, you've got some headers. Bodo, Amazon's S3 library, for some reason, ships with 42 megabytes of JSON that describes how it talks to the Amazon API. I don't know why they did that. And you've got a bunch of other crap, right? Oops, But the point here being that these take up a lot of space, and there's no way we're ever really going to get these onto or inside of a Lambda. So instead what we did is we hacked the dynamic linker. So we now have our cool dynamic linker. It's kitschy. And what we do with our custom dynamic linker is it works exactly, it's just a modified version of LDSO. But what happens is when the Python interpreter calls import sklearn, same thing happens, dlopen, blah, blah, blah. But our custom linker goes through an external Python process to pull any of these shared objects from S3. They come back in, they're copied directly into memory, it's fine. Because the neat thing about Lambdas is while you only have 512 megabytes on disk, you have 3 gigabytes of RAM. So you have a lot of actual space. And that lets us put in all of these extra shared objects. And what that means is that this original runtime here, which on disk would have taken up, got blown far past our 512 megs, right? Now looks much more like this. All those shared objects are gone. We fit, things work perfectly fine, right? This is less than 512 megabytes. You would think I just started using a presentation package with my enthusiasm for that effect. What this results in is much more capable dynamic default runtimes, right? So this means that no longer will you have to say, oh, make these sorts of trade-offs. Well, I was going to use pandas, but that means I can't use scikit-image, right? The hope is now you'll be able to kind of, by default, use everything. And that's alluded to coming in a release that we're trying to push out right now. Now, that's fine, but what are the opportunities for going kind of beyond these sorts of map-like workloads, right? So this is also, so PyWren was originally written by me in a weekend when I was like, what's a crazy, stupid thing I could try and do it with Lambda? And let's see if Amazon will yell at me. And NUMPYWREN, which is this project, has a little bit of that flavor, where one of our very bright graduate students, Vaishal, was like, well, is it possible to actually do kind of large-scale HPC-style workloads on Lambda? And again, let's talk about the wrong tool for the right job here. But it's interesting because linear algebra underlies effectively all of our modern computing infrastructure, right? There's this whole domain of HPC that many of us are familiar with where you get a big supercomputer and they have custom high-speed interconnects because you want to solve these very large kind of matrix problems. But there's also this exciting machine learning universe, right? Now, everyone's very excited about deep this or deep that, But back in the day, we were very excited about being able to just do things like large-scale matrix completion or large-scale singular value decomposition. And Chris Ray at Stanford has this nice quote where he says, "It's easier to train a deep neural bidirectional LSTM with attention than it is to compute the SVD of a large matrix." And as a machine learning researcher, you really feel this, right? Taking a large SVD is hard. It's a thing that requires kind of all this complicated technology, whereas you can pip install TensorFlow and do kind of all these amazing deep models. And so the question is kind of, how can we make that easier? And we kind of noticed 4 trends, right, in computing right now. One is that kind of compute is becoming more precious, right? So call this No More Free Lunch. This is from David Patterson's book, and it shows the kind of growth of single core performance as a function of time, and since like 1978. And this graph is actually what keeps me up at night. I mean, this in many ways encapsulates my life. I was very young there, I got married there, and this exciting 52% a year growth period was my very formative kind of teenage years, right? So that's how I expected the world to be, and it's not. And what that suggests is that if compute is becoming if our rate of compute improvement is slowing, then relative to everything else, compute is going to become more valuable. And thus efficiently using compute is going to become more important. And there's also trends in data center disaggregation that everyone's seen, right? So let's look at the cost to store a terabyte, right? If you want to keep a terabyte in RAM on one of these large Amazon instances, it's like $6 an hour. If you want to keep a terabyte in S3, it's 4 cents an hour. And of course, these are very different pieces of infrastructure. But the amazing thing that again, Vaishal has found through extensive benchmarking with Lambdas is that you can actually get pretty reliably, let's say 60 megabytes per second read and 50 megabytes per second write to S3 per Lambda. But because you can get so many Lambdas, you end up with these, this is just a runtime plot over time of spinning up a ton of Lambdas. We can get aggregate 300 to 400 gigabytes per second. Again, gigabytes per second of read to S3 and about 200 gigabytes per second of write. That suggested maybe it might be possible using this large-scale distributed Lambda fabric to do these kind of high-performance computing operations using S3 as our kind of intermediate memory or backing store. The other interesting thing about a lot of these HPC-type operations, right, a lot of these large-scale linear algebra operations, is that their parallelism, their opportunity for parallelism changes over time dramatically, right? So blue is the maximum number of simultaneous threads you could run, right? And red is the working set size. And you see that, unsurprisingly, if you're trying to do something like a large-scale Cholesky factorization of a matrix, the working set decreases as a function of time, but the number of threads you need, right, the opportunities for parallelism varies dramatically. It's this dampening sinusoid. What that means is that if you're using traditional HPC tools like MPI, you either are going to kind of take the outer hull here and have a bunch of cores sitting around idle, or you're going to pick some middle spot that's maybe a trade-off there, but you're not going to get the speed you want. So we thought, how can we more efficiently use something like Lambda to target that? And the other nice thing about these linear algebra operations is that compute is cubic, but storage is, of course, quadratic, right? Solving a matrix like this is an O(n) cubed operation, but when you are trying to do I/O with these things, you're just moving around blocks of a matrix. And again, what that suggests is that for all of these sorts of operations, maybe having a more expensive communication bandwidth bottleneck isn't that big of a deal, right? So our goals with NumPyWren have been kind of no expensive setup, just like PyWren, right? We would like for this to be kind of as transparent and usable for both us, because we're lazy, but also for all of our collaborators as possible. We'd like to really take advantage of this idea of decoupling compute from storage, right? We'd like that things to basically run as fast as they possibly can, using as many cores as they can when those opportunities for parallelism arise. And we'd like to basically, if your available storage increases, we'd like for you to be able to run larger jobs, right? There's this notion of, we've been calling it kind of elastic parallelism, right? We'd like to be careful with compute. If cores are expensive, and if you can get cores that are metered on kind of a tens of milliseconds to hundreds of milliseconds scale, then using them more effectively might result in systems that are more cost effective. NumPyWren is built on top of this intermediate representation called LambdaPack that Vaishal and Carl have been working on extensively with a large number of other people. And at the end of the day, kind of calls out to PyWren. But the goal of the NumPyWren interface here is to kind of be usable by anyone who uses NumPy, and basically have all of these matrices stored in S3 as transparently as possible, right? Again, all intermediate state is retained, and maybe I'll talk in a bit why that's useful. But let's take an example like nearest neighbor search, right? So this is just a normal kind of thing that you would imagine writing in NumPy. And the nice example here, right, is the red parts of the new code that you have to write. You have to create this NumPyWren executor. You have to kind of initialize these NumPyWren matrices that are going to magically and transparently live in S3. But then everything else, you're just basically replacing the equivalent NumPy call with the call to this NumPyWren executor. Oops. And then we have a return. Right? So let's take something like solving a linear system, right? Least squares is still a thing that many people do in this world, in spite of what Jeff Dean might tell you. How do you solve a large system like this? Well, often you compute some matrix factorization. You do something like compute the Cholesky factorization. And then you do a couple of forward and backward substitutions. And again, the primary killer here is this n-cubed operation. And this decouples very easily into a series of local block updates, right? And there's been all this work by people going back 40 years on communication avoiding algorithms for these sorts of things, right? Where you basically do one update, and then you kind of do a broadcast, and then you do another update. And with an eye towards time here, we end up using NumPyWren takes advantage of Lambda for the compute, S3 for the storage, and SQS for the control flow. And it does this by spinning up a very large number of Lambda workers that are going to take kind of effectively these little instructions for block matrix operations from this larger instruction queue and run kind of simultaneously a collection of S3 load, kind of a Cholesky operation here, and then S3 write operation on each of these. And we pipeline them in a way to get kind of maximum efficiency, right? But the takeaway here is that the per core kind of network and compute capabilities inside these Lambdas are actually incredibly powerful. And let's see how that actually looks from a performance perspective, right? So there are two ways you can imagine a system like this measuring performance. One is efficiency, right? How efficiently did I utilize my resources? And if you're the sort of person who gets the Amazon bill each month, like my advisor Ben Recht is, that's something you probably care a lot about. There's also this kind of end-to-end runtime question. How long did it take to get an answer? Kind of how many episodes of The Good Place could I watch before I had my solution? And so if we look at the total core seconds used between, say, NumPyWren, ScalaPack, and what the theoretical lower bound would be for doing one of these large operations. So problem size down here is in 128 2D. This is the dimensionality of the matrix, right, on a side. And the y-axis here is compute times in millions of core seconds, right? And remember that graph there is that graph layer is logarithmic. So we see that kind of in all cases, NumPyWren is getting kind of suspiciously close to the total, the theoretical lower bound, and doing better than ScalaPack. Now, why is this, right? This is because ScalaPack has kind of commingled compute and state in this way that you end up having to keep up a bunch of extra cores that are basically just sitting there being impatient, right? But of course, now there are trade-offs. Let's look at total kind of completion time, right? So again, this is that end-to-end time I was talking about, again, for these different problem sizes. So here we also compare with Dask, which doesn't do great at large scale. But we see that, and this graph here is not logarithmic, right? So we see that NumPyWren is actually going to take you, let's say 10 to 15% longer, right, in terms of watching your clock, watching your watch for a given compute operation, but with kind of dramatically enhanced efficiency. And that's really the goal. So NumPyWren, I appreciated the comment that in the intro that the paper was published. It is not yet published, it is submitted, which is a very different state of the world. But hopefully will be published soon, and we're putting it up on the archive next week, and we're trying to get that code in a releasable state as well. Because again, the goal of these class of projects is to kind of make these tools accessible for a larger audience and take advantage of these kind of changing computation trends ranging from disaggregated storage to the increasing effective cost of compute. Today's exercises. We're going to go through, there's a nice intro in the IPython notebook that you can walk through. Don't just hit Control-Enter on every cell because there are things that you need to fill in. There's one where you go through and analyze the Wikipedia content because, of course, every map-related thing requires you to do that. There's some hyperparameter optimization. One of the cases we often use NumPyWren for, or for PyWren for, is kind of large-scale exploration of hyperparameter spaces. And then there's a little bit playing around with some of these matrix computation ideas that we talked about. So with that, This is not me. This is a very large team of people who all work much harder than I do. In particular, we have two great new undergrads, Vaishal and Carl, and Shifan are kind of singularly responsible for almost all of the actual work that happened in NumPyWren. Shivaram, who has been at many of these RISE retreats like us before, is now a professor at Madison. And then Jan, Ben, and JRK are the kind of adults keeping a lid on things. So the goal of PyWren is very much scale for everyone. We hope this next generation runtime stuff is going to really ease capabilities for a lot of people. NumPyWren paper just finished, and we're hoping to get that into everyone's hands relatively quickly. So I encourage everyone to come to the RISE retreat where you'll get to play with that. See what I did there. And the hope is to have this bug fix out by Halloween, because spooky releases are the best. And other than that, enjoy the tutorials and let me know if you have any questions. Oh, also, there are TAs to help with the tutorials. If you get stuck or having trouble getting started, the lovely people over here on the right, stand up guys, will be wandering around to help. So feel free to ask them any questions about basically anything.
Quick question. How does PyWren compare to Ray?
Who was that? Where was that person? Great.
Hey, this is Shreyas. Hey.
I know where you are now. So I think of Ray, right, what is there's some official party line I'm supposed to parrot here. But I think of Ray as the thing that you should use if you actually want to build a real distributed system, if you actually care about latency, or if you actually have kind of more complicated computing primitives, right? So Ray is very much the thing that I would often turn to many of my computer science colleagues and say, this is the tool you should use. If you care a lot about kind of the elasticity part of this, and if you have a lot of things that look more like ad hoc workloads, I think PyWren and its ilk are potentially a better fit. Other questions? Yes, sir.
You mentioned Google Cloud Engine and Azure in addition to AWS, but then you mainly mentioned AWS later on. So I'm wondering whether all the features you described also work in the other clouds?
So we have experimental work on getting everything to work in the other clouds, right? We've successfully run a job and that sort of thing. That said, and I'm sure there are representatives from Azure and GCP here, so please do not find me afterwards. But their offerings on the function space are just less mature. Right? The number of functions that you can get in a given invocation is much smaller. The kind of runtime parameters are different. So we have not had the same success with Azure GCP that we have with Lambda. That said, actually, we would love to work with those groups to kind of push that more forward. The place we've had the most success that I didn't bring up, and there's been a lot of real great work by IBM on extending PyWren to running on OpenWhisk, which is their kind of, it's this Apache project for kind of function as a service in kind of internal deployments. And that's actually been great. I mean, OpenWhisk is really nice because it basically lets you just run a container of whatever, wherever. And that model fits very well with PyWren.